Okay, so if I say E of x, let's call this as mu. Okay, it's okay, mu, right. Then the variance is defined as, well, there's a formula for the variance as E of x squared minus E of x squared, but in its original definition, if you look at the definition, it's like xi minus mu squared pi, right? That's our definition. But if you look at what this is doing, it's really, this formula is really calculating the expectation value of x minus mu squared. Right? X minus mu squared. What does this measure? It looks for the center of the data, center of the probability distribution. What does this measure?
Spread.
Spreadness. Okay, if this is big, it means that the data is spread wide. If this is small, data is packed together. Now, there are other powers. So there's something called skewedness. Which is E of x minus mu cubed. Now let's think about why this would be called skewed. So if you have, let's say this is mu. If your data has more stuff on this side, actually. So data should still be peaked somewhat here, but then let's say you had more stuff here, or think about there being some. Not doing this. Okay, think about a skewed data, something like that. Okay. Now, by the way, this one is called the right skewed. Because the foot of the data is extended to the right. Okay. You don't look at the peak, you look at the foot. Right? That's called right skewed, and then if it's like this is called left skewed. It's important that you know this, okay? So if you look at the right skewed case, the average will be somewhat a little right of the peak, right? And what happens is that the values, there would be outliers on the right side, and these values would have a very big difference between the mu and the value itself. And because you're taking the cube, it's going to make it very big. Do you agree? The cube will make the difference between these two to be very big. So what's going to happen? If this will be a lot bigger than the other values, so take the difference between this and this, that's small, take the cube. It does become bigger, but not as big as these differences. Take things in here. It'll be x minus mu will be a negative value. Taking a cube, it will still be a negative value, but that negative value won't be as big as this. Right? So you kind of see that if it's right skewed, this outlier on the right side will make the entire value to be positive, because this kind of overpowers the other ones. Does that make sense? Especially the ones in the negatives won't be that big. Okay? On the other hand, if it's left skewed, then your outliers are on the left side, and the difference between x minus mu will now be a huge negative value. So that if you take a cube, it will still be negative, right? And it will overpower the other ones. So in that case, this value will be negative. So the skewedness measures which way the data is skewed. If it's right skewed, this value will be positive. If it's left skewed, this value will be negative. Okay? And then there's something called kurtosis. fourth power. And this one also looks at the outliers, except that the difference between this one and this one is that this always is positive, right? Here, this skewedness could be positive or negative, but variance and kurtosis can never be negative. This could be negative or positive. These are always positive. And what it does is that we haven't done normal distribution yet, but there's something called the normal distribution, which is like the most important distribution of everything that you've learned. It's like the bell-shaped curve. It's the most prevalent one. You see that a lot of them happening. And for the normal distribution, the kurtosis, for the standard normal distribution, the kurtosis comes out as 3. So there's like, of all the bell-shaped ones, there's a special one where average is at 0, and then variance is exactly 1. It's called the standard normal distribution. If you calculate the kurtosis of that, you get 3. And then what happens is that if you have another distribution where it has a fatter tail, meaning more outliers, then the kurtosis will be bigger. If it's somewhat faster decreasing tail, then the kurtosis will be smaller. That's a pretty important aspect that the financial analysis, like stock analysts, are very interested in, because the stock prices, although it looks like a bell-shaped thing, sometimes the stock price goes up, sometimes goes down. If you look at the daily ticker price, whether it went up or down, it kind of looks like a bell curve, but it's not the normal distribution. It has a fatter tail. In other words, there's some more volatility than the regular normal distribution. So they talk about, they would look at such a thing. And unfortunately, they think that for the stock market, the kurtosis actually becomes infinity, which means, it's this whole different discussion, but something like that. Okay? And people look at these values to make a judgment of how far off the given distribution is from the bell curve. So the standard would be, if the skewedness is very close to 0 and the kurtosis is very close to 3, after making it, normalizing it, then you're kind of happy. Oh, that means we have a very good bell curve. We can apply all the statistical knowledge that we know of the bell curve. If it's not those numbers, then you start having some doubts. Okay, so these values in general have the following form, and those are called moments. Okay, so the nth moment centered at C is given as, it's called mu n, which is the expectation value of x minus mu, x minus c to the nth power. So you see that the skewedness is the third moment centered at mu, and kurtosis is the fourth moment centered at mu. And we put subscript n. So although I'm using the same mu, unfortunately, people use mu because of mean. This is a Greek letter for m, right? So mu is mean, but people also use mu for moment because it starts with m. So that's, you're stuck. So sorry. Now there's two special cases. If c is the average value, or the mu, we say mu n is the central moment. Okay. And then if c is 0, we say mu n is the raw moment, and we often use prime to distinguish the raw moment. Okay? So if you think about the following formula that we keep referencing today, that the variance is e of x squared minus e of x squared. This one is what? This is exactly this formula, but instead of this, you have 0 there, right? So that's a raw moment. So that's going to be mu2 prime. That's being squared. No, mu2 prime itself, right? Sorry. Minus, what is this? This would be like this with n being 1, with c being 0, x minus 0, right? E of x. So this is going to be mu1 prime, but then there's a 2 outside. So that's the variance. Moment generating function is by definition e of tx. I guess that's simple enough. They didn't name it using a different letters. It's just that. Okay. So let me see if you remember. Yes.
That's t times x, right?
Yeah, it's t times x. It's tx. Okay. So let's see what this really means. So what is that? E of tx is, by definition, if you have any function of x, you just put that into the sigma, except you just replace x by xi. That's all you do. That's called the, what is that called? The law of unconscious statistician. Add e of txi times pi. That's what it is. Okay, so let me see who remembers what we did last time. Do you remember the Taylor series of E of x? Do you remember the Taylor series of E of x? One plus x over 1 factorial plus x squared over 2 factorial, x cubed over 3 factorial, and goes so on, okay? So we mentioned that. And what I want to do is I want to just replace this x by txi. And then I'm going to just plug this into here and get this gigantic series, which is sum of 1 plus txi 1 factorial plus xi squared. I'll write like this: xi squared t squared over 2 factorial, xi cubed t cubed 3 factorial, so on pi. And then, do you remember how we differentiated both sides to show that this thing doesn't change much, right? Because e of the x differentiates to e of the x, right? Okay, so here's a question. If I differentiate e of e to the tx twice, differentiate twice, that's just the way of saying differentiate twice, and then plug in t equals to 0, what would you get? So differentiating 1 twice, what do you get?
0.
We're differentiating by t. Okay, these are just considered as constants. Okay, so if you differentiate t twice, what do you get? 0, right? T once, you get 1, but if you differentiate again, you get 0, right? Yeah. Come on, you would like it if you had the same question in Calculus 1, don't you? Like if the final exam question is, find the derivative of ct. I mean, yay, I know the answer. It's like c, right? If you differentiate twice, it's this. I'm asking a very simple question. Everyone knows this, okay? All right, so you have that. How about this one? If you differentiate twice, if you differentiate this twice, what would you get?
1.
Once you get 2t, right? 2t over 2 factorial. What's that? T, right? But then you have to differentiate again. What do you get?
1.
1. You just get 1. This just becomes 1. And then the other ones will get, I mean, this one will differentiate to what? It will be just t, I think, right? 3 comes down canceling the 3. Another derivative will cancel the 2. So you'll end up with t over 1 factorial. It's just t. But the important thing is everything else following will have some t there. Okay? This one wouldn't. This will be constant. These will be just 0. So what is the only non-zero thing you'll get after you plug in 0?
T.
Which one will be the only survivor if you differentiate twice and plug in 0? This will be 0. How about this? 0. How about this?
1.
This will be 1, so you're just going to get that, right? How about this? It will still have t there, so when you plug in t equal to 0, it's going to be 0. Everything afterwards will be 0 for a different reason. T plugged in by 0 will make those gone. It's not there. So what you get is summation of xi squared pi, which is, what is that? What is this? It's E of x squared. Right. Which is mu 2 prime. It's the raw one, right? Okay. So if you follow this once, then you kind of see what's going on. Oh. So if you can figure this out for some reason, there's some, you just have to work a little bit, but there are some cases you can actually figure this out. If you figure this out as a function of t, then you can find all the moments for free, because you just have to differentiate, plug in 0, and that's it, okay?